Let's get a little practice at the sign convention that goes with Mohr's circle by actually then executing one of these as well. So we'll get a bunch of things all at once out of this particular exercise. Right? So we're given a state of stress where on one plane we've got 1,000 psi normal stress. The other plane we have a 2,000 psi normal stress, and on both of those there's a negative 500 psi shear stress. All the arrows shown here are, of course, associated with the positive sign convention, right? So remember, in Mohr's circle, the first thing that we really want to do is label a couple of points that are at 90 degrees to each other. So let's start with the one that has an outward normal that goes to the positive x-axis, and let's just call that point A, right? And so on that surface, we have a 1,000 psi stress that is positive, which means it's in tension, right? The shear stress here is 500, but it's negative. So the positive direction on that plane would be physically going up, but since it's opposite, that means it's acting the other way, other direction, and that means it wants to spin the whole thing in a clockwise direction. So that would be 500 clockwise. And now let's plot that. Now on our Mohr circle axes, we've got the normal stresses on the horizontal and shear stresses on the vertical. Tension will go to the right, compression to the left. Tension is the positive, compression is in that negative direction. For plotting purposes on Mohr's circle, clockwise shear stresses will go up and counterclockwise will go on below, right? So I remember that by clockwise has 2 letters, counterclockwise has 3 letters. More letters, heavier, sinks. That's how I remember that, right? So point A, we go out to 1,000. So I think I'm going to make each one of these little tiny hash marks 500, and then I'll go up 1 hash mark, so another one there would be 500, and there's our 1,000. And I'll plot that point. That's point A. Right? Then let's get another point that's on the other surface, right? The other surface is at 90 degrees. We got 2,000. That also is in tension. And then we have 500. Again, it's the opposite of what's shown. What's shown is one that would tend to go clockwise, but it's opposite of that. So it's going to want to spin that block in a counterclockwise fashion. So 500 CCW will be point B. So, all right, go out to 2,000, which would be out to here. And then it goes on the other side at 500. And then that looks to be point B. Remember, these two always have to be on opposite sides of this horizontal axis, and they have to be exactly the same distance away from that axis. And that's because for equilibrium, those shear stresses always point together. So that automatically makes the opposite side part. And for equilibrium, they have to be the same values, right? Otherwise, the thing will spin in an uncontrollable fashion, right? So opposite sides and the same magnitude. That means this circle has to be centered on the horizontal axis, not on the origin, but has to be centered on that horizontal axis. And in fact, A and B are diametrically opposed. I mean, they're just on opposite sides of the circle. So we can draw a diametric line or a diameter, and where it intersects here will be exactly where the origin of the circle is. What that really means is the average of those two, 1,000 plus 2,000, accounting for sine. Oh, wait a minute. Well, 1,000 plus 2,000, that'd be 3,000 divided by 2. That would be 1,500 is where that center of that circle is at, which does mean that then this triangle that goes here and here turns out to be at equal distances in this particular case, 500 and 500, right? So actually we know right off the bat what that angle is going to be. It's a 45-degree angle, right? But that's getting a little ahead of ourselves. Let's just focus on what's going on here. If that's 500, that's 500, and that's 45 degrees, well, then we know how to find this. It's 500 times the square root of 2, right? Which will turn out to mean that this radius here is 707 and change, but that's what it'll be, 707, right? And that radius then needs to get swept all the way around in the circle to create more circle. And that's going to give us the state of stress on any plane that we would want. All right, so I'm going to do that in blue here. And so I'm freehanding. Now, you don't really want to freehand, right? What you want to do is get yourself a circle template. This little template right here, it's a barrel rapid design template, number 140. It's what they call the large circle template. You can get much bigger ones. You could get a compass. I say use a template that's far easier to use. This one has as a maximum here a 2 1/4 inch diameter circle. Goes really down low. These will be in here will be the ones that you're going to use most often. Right? Your high quality circles will come from a circle template. We're not going to freehand. I'm going to do it freehand here because I'm on the whiteboard. Right? So I'm going to mark off here about 707. There's my 707. Come up here, put a little point, and so on forth. It looks like I'm a little off here as I'm sweeping this around. Put a little 707 there. Oh, wait a minute. 1500 plus 707 is going to put us out at around 2207, right? So that'd be about out in here. So our largest value is 2207 over there. 1500 minus 707. Well, let's see. 1500 minus 700 is 800 minus another one. So that's 793. So we're right about down in here at 793 for that part of the circle. A little easier now for me to draw at least the top half of the circle. That's not real great. Let's try that a little again. And that's why I don't want you to do it freehand. Do all that same kind of business down here. Right? And there's our plot of Mohr's circle. Now, gee, why the heck do we do all that? Well, we can now easily identify what those maximums are. Those are called the principal stresses, right? And the largest one is called by definition, the largest one, which means the largest algebraic value, not absolute value, but largest algebraic value is P1. And that's going to be, in this case, a plus 2207 psi that is in tension. Your smallest one is the 793. It's also positive, which means it's also in tension. Now, we get more out of this than just simply those magnitudes. We now know also where exactly it is oriented. And so let's look at what's going on here. From point B over to P1, right there, on Mohr's circle, is that angle right there. Right, so from B that way. Now that's twice the angle, right, because it's Mohr's circle, so 2 theta. Now we know this whole thing, we measured it, we know it's 45 degrees. So that, of course, means theta is equal to 22.5 degrees. It's measured from point B. Now point B, which I forgot to note on our stress block way back long ago, is this one right there. Right? So what that means is when I look at our stress block, there's your point B, and I'm going to rotate it what? This way, 22.5 degrees in real life. That way is, of course, counterclockwise. It's going to go like that. So when I put this post-it up here to get and draw the stress state that we have, then we start there from point B, rotate that 22.5 degrees, right? And so it looks like that. And our sigma P1 is on this plane. That's your 2207 psi, right? That's right here. Now, if I want to get to the opposite one on Mohr's circle, I go all the way around. How do I know that? Well, from here to here, the outward normal swings 180 degrees. 2 times 180 is 360. So in Mohr's circle, I sweep from that point all the way around 360 degrees, end up at exactly the same point, and there's your 2207. We have to have that for equilibrium, right? Now, the other piece of that is, well, what's the shear stress on that plane? But the coordinates right at that point are, well, XY, right? That is 2207 tension, comma, 0 for the shear stress. Bam, that's, oh, there is no shear stress. That's right. On the principal planes, absolutely by definition, there's no shear stress. That's the maximum normal and 0 shear stress. Right now, to go from point B over to the other one, the 793, we could do it this way. That would be 135 degrees divided by 2, right? So 131, it's going to be 67 and a half, I think, right? Or we could have done it this way, right? We got to go from A and go that direction. Of course, that's 45 degrees again, right? We're sweeping 45 degrees. That'd be 22 and a half degrees from point A. Where the heck is point A? Point A is on this surface, and we're going then and rotating from that one, 22 and a half. Oh, it's just this one right here. That's all it is. And that's 793. Boom. So that would be technically this one, and then we swing all the way around to get to the other side, and again, it's 793, and that will give you the maximum normal stresses, what we call the principal stresses, and those are effectively the 4 principal planes. Really, we think about it as just 2 principal planes, but really from a block standpoint, there's 4. Right, now that gives us the maximum normals. For the maximum shear stresses, then on Mohr's circle, right, we could be anywhere. Oh, well, the maximums are out here on these outer edges, which is right there and right there. Right, top and bottom of the circle. And that radius we already know is 707. So the answer for the stresses is 707. Now to get the properly oriented stress block that represents that, then we have to do the same thing that we did before, right? And so we can start here at B and go down to it. That's cool. It's the same thing we did. It's the different 45 degrees, but it is just 45 degrees. And it gets 2 theta would be equal to that 45 degrees. Now, some people would start calling these P's and P1, P2. It depends on how you're measuring it. They call that one a theta S to get to it. I hesitate only because that's really, when you use those designations, they're coming from point A, right, that X outward normal. But informally here, we can play with that. Of course, that means 22 and a half degrees again from B over there, and so B was on this plane here, and we went and rotated a Mohr's circle in a clockwise fashion. So it's going to rotate like this, right? And let's see, now the block rotated that way. The value is 707 counterclockwise, so that would be that direction at 707. Once you do one of them, the rest of them have to follow. The opposite one has to be in the opposite direction, and then they have to pinch together. You can actually very quickly get all those. Now, what's left off here, though, are the normal stresses that go with this, right? Point B came down to here, and the normal stress was a value of 1500 in tension, right? That was this one. So we got to get that as well. And note what's going to happen here, that the normal stresses are all the same on both of those sets of planes, right? Because we're right here, those coordinates tell us what the values are of both the normal and the shear stress, and we're right there vertically opposite of each other, right at the center of the circle. So they're at 1500, and that then will be our maximum minimum shear stresses. And I think for completeness sake, we ought to at least write that down. Tau max equals 707 psi. And then the normal stresses associated with that are both at 1500 and in tension. Right? So wow, that's a whole lot of things. So let's do one quick review here in the sign convention of Mohr circle. One, you got to start with, and I usually start with a stress block with the stresses showing the way they physically are behaving. This one goes from the absolute sign convention associated with the stress equation. I'd rather, because I got all this flippy floppy business, I'd rather just show them the way they're physically acting. And then on Mohr's circle itself, the plotting, we got tension to the right, compression to the left, clockwise for the shear stress above, counterclockwise for the shear stress below. And the advantage of that is, as we march radial lines around this circle, that's exactly the same direction that we're rotating the stress block as we go from various points over to then the plane or the point of interest. If you don't do that, if you do an absolute mathematical sign convention, this whole thing gets flip-flopped. And in that case, when I rotate around Mohr circle on Mohr circle, that's opposite of what we do in real life. Now, that's the way I learned, and I figured it all out. However, it is easier to not have to do just one more thing, because, gosh golly, we've got a bunch of coordinate systems. We've got the regular old right-hand coordinate system that you're used to from an X and Y world, right? Then we've got the state of transformation equations. Oh my gosh. Then we've got more circle equations in how to interpret, and we got the plot itself to have to interpret. That's a lot of little pieces running around, and it's not easy to keep track of all those little sign conventions. That's why I like to have these Post-its, nice and colorful ones for me. And I write this kind of information down. If it's the stress transformation equation, I'll write that sign convention down. If it's Mohr circle, I'll write that down. And I'll just keep all this stuff all handy. It makes it so much easier to keep track of what you're doing in any one particular situation, because it's complicated to keep track of all that. All right, let's get ready for some more examples.